There we go. So hopefully we're ready to get going. So I'm still in Halifax. My wife is down in Kingsburg with Dora for this week and next week. But this is from during the break week. This is the Kingsburg Pond, which sits back along this shore. You've got nice beaches, and then you've got like a big sandbar, and then frequently a pond that's in behind that. This is the pond at Kingsburg. And it was just freezing over. And here we are. This is actually last winter when it froze over much earlier. And folks, they set up chairs, tables, all that sort of thing, and would go out skating on the pond. It was very much a family affair. It was a fun time. But, few announcements. I should mention a few things. The Enactus team, I've told people, get yourself involved. That the regionals were held last weekend. And there were two categories, two challenges. One was in climate action and one in entrepreneurship. And our teams won in both categories. And several students that are enrolled in 1206 were part of the teams. So congratulations to them. And I should also mention that our women's basketball team, of which we've got at least one player on the team this term, and they won the Atlantic University Sport Championship and are on to the nationals in women's basketball. Congratulations to them too. So this is Wednesday, and Wednesday, I may mention before, it's International Women's Day, and good reason to celebrate and reflect on well, what we could do to make this actually a better day. But it's also World Maths Day, so that's for geeks like me, and some of you maybe that are geeks as well. So let's get going. That we've got a discussion due today, as usual. It's Wednesday. Assignment 3 is due on Friday. That I'm recording this on Tuesday morning, so this afternoon I'll have done the tutorial for the assignment, and I encourage you to use it to help you get through the assignment. But once again, I remind you, please try each question. If you get stuck, watch that segment of the tutorial and then turn off the tutorial, go back, work at the problem, and go back and forth, and do it in that fashion. But don't watch the tutorial before you've tried it yourself. And we've got a quiz due on Saturday for this chapter 8 that we're on right now. I think it's chapter 8, isn't it? So we started classification last class, and we'll do classification again today. That next week we digress and look at probability, because we need it to understand a number of things about classification models, especially when we do evaluation, which is in chapter 11. But also some of the methods for doing classification. I wouldn't say the methods, well, some are actually based upon basic probability concepts, but some draw from ideas of how we solve probability problems. That type of strategy can be transferred to looking at strategies for handling other types of problems, such as classification. So in classification, we're trying to predict a categorical variable. And sometimes it's an ordinal one, but most of the time it's just a binary variable. And so it's yes or no. Are you in this group or not in that group? And sometimes if it's more complicated, we do it by splitting you into different stages. Like, are you going to renew your cell phone plan or not renew it? And then if you renew, so if we pass through that classification, are you going to keep your current plan or do you plan on changing it? And then we could even go and look at if you're going to change it, what type of changes there'll be. So we can have a sequence of classifications that would then cover nominal variables that have many categories. We could do as a sequence of binary ones. The challenge, and I can't emphasize this enough, and people get confused on it, is thinking about accuracy, because we've spent a lot of time on value estimation talking about accuracy, R-squared, standard errors, those sorts of things, which are really important. But when you're looking at classification models, all of that stuff goes out the window. It's quite different. Now, our decisions, our actions, our classifications are either correct or they're not correct. So our measures of performance, and there are a lot of different ways you can measure performance, a lot more than with value estimation, is in terms of how often you're making the right choice. That's at least one of the most common methods. So what percentage of your classifications are correct? Sometimes it's the positive ones that are more interest to you, and sometimes it's the negative classifications that are more interested. So if you're looking at fraud detection, it may be the percentage of fraudulent transactions that you were able to detect. Or if it's valid transactions, what percentage of them did you get correct? Or maybe more importantly, of the valid ones, what percentage did you classify incorrectly and got upset customers? And you have to think in terms of the consequences. And that becomes sort of your focus. What are the consequences of making good and bad decisions and the different types of decisions? And from there, you tend to prioritize what performance measure you use. But all of that's going to come up in chapter 11. Among the methods that a lot of them focus on estimating the probability of a specific outcome. And then given the probability, we decide on taking an action, yes or no. And so it's in a two-stage process. And last time we looked at how could you estimate that probability. But it's also equally important to understand that you need to come up with an appropriate decision rule. And that's not automatic. It's not a 50% cutoff like we used last time. It can vary as to where you want to put the cutoff. Depends upon the consequences of making right and wrong decisions, actually. Just to hammer this home, we do this on a regular basis. Now, this is taken from last fall, and it was, I had happened to check the weather network at 5:30 in the evening, and then I did that on my computer, and then I said, well, what does my phone say? And my phone uses AccuCheck or AccuWeather, and that it was strange what happened. So if you look at, this was a Sunday evening, and for 6 o'clock, the weather network was saying it's cloudy and maybe a 30% chance of rain. And if you went to AccuCheck, it said it's going to rain, and with a 56% chance, different probabilities. That the at 7 o'clock, that they gave a different prediction. Both of them were saying rain, but they had different probabilities. Now, Weather Network jumped to 80%, and AccuCheck stayed at 63. So obviously they're using different models to estimate the probability. And both of them tend to use 50% as their cutoff between saying it's going to rain and not rain. And you can see they also they did value estimation. They predicted what the temperature would be, and that they came up with different predictions there. They use different models. Same data though, but they have different models as to how they do it. I also find it interesting that the Weather Network rounds their probability estimates to the nearest 10%, and AccuCheck gives it to 2 full digits, the 56 and the 63, instead of saying 60% chance. The Weather Network would have just said 60% chance in both cases. So different attitudes in terms of how they communicate information. Myself, I prefer the Weather Network. I think it's more honest. These estimates are very, very approximate. They're not super accurate, just like you see how different they are between the two of them. On some, like the 6 o'clock forecast, the one that was going to be in half an hour. That if you can't be really precise, then giving 56% suggests precision that probably isn't there. They should have just said 60% and be done with it. But these are predicting rain is a classification model that's based upon estimating probability and having a decision rule. So this is one we see regularly. And then you may make an additional decision of whether or not you take an umbrella with you. And you might only do that if you think it's an 80% chance. It's up to you. So last day, we did look at using value estimation models to estimate that probability, and that is a common strategy. And we've looked at one method, multiple regression, that looks at straight line models. And but what we're trying to predict is rain or no rain, the probability that it is either 0 or 1. And we don't have historical data on actually what the chance was, because if I look at the historical data, even though the weather network may have predicted a 30% chance of rain, it either rained or it didn't rain. Turned out it was really heavy rain. So what gets recorded is rain or no rain. We don't observe a 30% chance. Maybe 30% of the time they're right, but that's a different thing altogether. So our historical data that we're trying to predict and use to train our model, our values of that y variable, the target variable, are just zeros and ones. We don't have historical data on probabilities because either the event happened or it didn't happen. Hard to get your head around, but we're estimating a probability, but we don't observe probabilities. But remember again, our objective is not to estimate a probability, but to do a classification. And so if we take, maybe we don't need precision in our estimates as long as they lead us in the right direction. So do they tell us to make the right decision? And that model actually worked quite well with the simple data set we have. And it frequently does lead you in the right direction, but I'm not sure there are better methods. So normally we don't use linear regression to do classification. We go and most frequently use logistic regression if we're using this type of model, this formula for probabilities, and building it like we would a regression model. And logistic is it's got this curve that's known as a logistic curve. The math behind it is messy, and I don't think you need to get into it, but you can see the concept there, that for low mass scores, we'd like to assign a probability of 0. High mass scores, a probability of 1. And somewhere in between, we have to make a transition between the two. And instead of you could do a step transition, sort of maybe at 370, you suddenly jump up to the top row. Turns out mathematically it's easier to work with a curve that exhibits that type of thing, that quick change. And we just, this one wouldn't necessarily make good predictions just on a mass score, but if we add in more variables, it'll help us differentiate that middle range of the mass scores. That other approach we looked at last time was building a fence, and a fence that would have the good ones on one side of the fence, the bad ones on another side of the fence. Mathematically, it's a lot messier than what I've got here, and especially as you get into more variables. But this is the basic concept of trying to build some sort of division between the two groups. And there are a variety of other methods that also do the same type of thing. And it can be a straight line, it can be a curve, can be more complex than this. We did it. I showed you this example of trying to use that credit card data we had and predicting whether or not you were a student using credit rating. And if you look at it, you can see that, hey, the students, they're the orange dots, are up above generally those that are not students. And as you recall, they borrowed $400 more. So yeah, we would expect the balance to be higher. But there are some outliers that we don't classify everybody correctly with this. It's rare that you get a very clean, perfect separation. There's still some noise there. But now I'd like to look at something completely different, just to get you thinking about, we don't have to solve every problem the same way. And there are many people that are locked into a mindset that this is the way we do things. I've always had difficulty both teaching accountants and working with accountants because they've got one way. of doing everything. And that trying to get them to be creative is challenging. Maybe, well, some creative accounting is legal too. So an interesting case is talking with real estate agents. And I've got relatives that are in that business and uh, others that I've been curious about. How do they do their work? And that they're going to try to estimate a selling price for a home. There's also a group called property appraisers that go and estimate the value of property so that you can secure a loan. The bank wants to know that if you're using your house as collateral and you're saying your house is worth $500,000, and so they should be able to give you a loan for at least $400,000, that the bank's saying, oh, should I believe you? Is it really worth 500? And so there are professionals that go through and try to give an assessment of if they had to uh, pull back the loan and take your property as collateral and sell your property to pay off the loan, would they get their money back? And so property appraisers do this in a professional fashion, generally for banks, insurance companies, and the like. How do they do it? Well, they look at um, similar homes in your neighborhood generally that have sold in the last few years and look to see how much they sold for. Yeah. So they're looking at other examples that are similar to yours. And neighborhood's really important. And then secondarily, other characteristics of the home. Location is probably the most important thing. So that's how they're trying to find similarities, and they're quite subjective in how they decide on that type of thing. They'll find 3 to 5 that have sold in your neighborhood that are similar. Hopefully there are some. And then they'll make some adjustments for special features. If you're living in a fairly modern subdivision, modern being it was built in the last 30 years, say, in that subdivision, there are lots of homes that are almost exactly the same as yours. So it's really easy to estimate there. Older neighborhoods are much more challenging. Like in mine, every house is different, that they were built over many, many years. And so it's a little more difficult to try to find ones that are really, really similar. In said new neighborhoods, it's quite easy because they all seem to look alike. Even then, though, it's not easy to do it. So it requires a lot of skill. They do it mainly in their heads, but can we actually formalize that strategy? And if we could measure what similarity means and what would be similar cases, like if I'm trying to decide, is this a good customer to make a loan to? Can I find 5 or 6 customers that are very similar to this current one? They have similar income, similar credit rating, a similar work history, they're similar age, maybe similar occupation, that, and then see what was the experience with these previous customers that look similar. And based upon them, make a decision on whether or not this person is a good credit risk. So it's really sounds quite practical, seems to make sense. And it's gotten known as KNN, or K nearest neighbor. K is the number of neighbors that you look at. So looking at who else is in your neighborhood. Neighborhood being defined as being individuals similar to you, past cases. I like it. Sounds similar. If we looked at this one here, where we've got the math and the verbal scores. So I take a new case, I throw it in there, and I compare it to the 20 that I've got right now. And I look for cases that look similar to this new one that I've got. And so I need to decide how many cases do I want to look at? Do I just want to look at 1 or 2? Or do I want to look at quite a few? Suppose I looked at 7. Just arbitrarily pick 7. And you'll see that 2 of them are very, very similar. And then another 5 are close. If I went to getting more than 7, I'm getting ones that are quite different in terms of their math or their verbal scores. And so I'll look at these ones, and if I was looking at 7, 4 of the 7 look to be good. So should I say that this is going to be a good employee? But look back at this one. The 2 closest cases were bad employees. So how many should I look at? I don't know. I've got to be consistent, decision to decision, and not just sort of flip back and forth. And how did I measure closeness? That even if you look at this one, I've distorted the scale here. You'll notice the verbal scores, the scale is short, and the math scores scale is quite long. I've stretched it. And so there's more concentration, in a sense, of the verbal scores. They look closer. Everything looks closer to one another when I'm looking up and down, and everything looks further apart when I'm looking left to right. How do I measure how close a point is to my new case? How do I make that decision? And then should I combine? Is verbal score as important as math score? We'll see there's a whole bunch of decisions you have to make to define what similarity means. So let's first look at distance. Sounds simple. That what's the distance from A to B? Well, if A was St. Mary's University campus and B was Pizza Corner downtown, what's the distance from St. Mary's to Pizza Corner? Well, if you're driving, you might end up, I don't know, driving down Robie Street until you hit Jubilee, going down there, hooking on to Sackville, and then heading from there down to Pizza Corner, roughly, or going via Spring Garden. For the most part, you drive north-south and then you drive east-west. So that's the dotted line there. We call that metropolitan distance or road distance. But if you could fly, or maybe if you were walking and you were sort of zigzagging, you could cut across things different ways, it might be what we'd call Euclidean distance, or distance as the crow flies from A to B. Which one should you use? You'll get different distances depending upon the way you measure distance. I'm not saying there's a right answer to it. I'm just saying it's a choice you have to make. And you'll get different answers depending upon which one you pick. And then we've got different units. So if I was looking at comparing two people, okay, they may have different ages and different incomes. Ages are in years. So how does the difference between being 30 years old and 40 years old compare to having an income that's $30,000 versus $50,000? It's about the same. Like the units are very different. And then if I looked at education, do I count it in years or do I look at it in categories? They've got high school, they've got college, they've got university. Gender. Well, even if the simplest way is male female, or you may want to cover more different gender categories, but you're of one gender, you're not in that gender, you're into a different one. So it isn't like a number, it's categorical. Same with employers. Did we take that into account? Yeah, if I was looking at making a loan, someone worked for the government, they got a really secure job, unionized position probably, versus they work for a new startup tech company that may be out of business in 6 months. So employer might be important to me because it reflects job security. How do I classify that? And if I was like predicting things like house prices, location's really important. How do I measure that? And it's not just latitude, longitude, because I'm looking at different neighborhoods. These are all completely different units. How do I measure things? So numeric variables, the most common approach that's taken is to standardize it, like making them all into Z-scores and saying how far above average or below average you might be. And and if I'm looking at the Z-scores, it gives me a standard measure, because it's not just my income is $10,000 above average. I want to know, is 10,000 a big difference? By dividing through by standard deviation, and that most z-scores are between like -2 and +2, they are the same type of units of measurement in many respects. So that's a very common measure. There's another one that involves looking at distance you are from the maximum, and then, maybe scaling things between 0 and 1. So are you at the very bottom, or are you at the top being 1, and looking at it that way. There's a variety of different scaling methods out there, but you try to then scale each of your variables so that they're some ways standardized. And it works great for numeric variables. It doesn't work as well for categorical ones because we don't have variability. You are that, you'd be a student or you're not a student. You're in one group, you're in a different group. So with binary variables, that it becomes tricky. Sometimes people set up rules and say, well, you're similar. It's a mandatory thing that if I'm looking at a female, then I'll only look at similar females. So you're in the group or not in the group. But if I've got quite a few different binary categories that I'm looking at, and that, or different categorical variables, I might look at, I've got 10 different categories: their occupation, their gender, their something to do with their health, whatever, a bunch of different categories. I might say, well, I'll measure how similar they are in terms of counting how many things they have in common. They're the same on 7 out of 10 characteristics. It doesn't it treats all characteristics the same, but maybe that's a similar way to do it. Um, uh, uh, it gets complicated though, and some of them have degrees to them. They may be ordinal variables, or even if I'm looking at hair color, it's degrees of hair color or eye color, that type of thing. It can get complicated. That's all I'm saying. That we're not getting into the weeds on this. And as I've suggested already, are they equal importance? Is knowing age as important as knowing income or knowing credit rating? When we're building our regression models before, that age wasn't that important, and number of credit cards wasn't important at all. So it depends. At the beginning, I looked at 7 different neighbors, and I thought, oh, that's tricky because the 2 closest were bad employees. How should I pick the number of neighbors? Lots of people say that we should pick an odd number so they don't have ties. We aren't going to get, okay, 4 out of 8 were good, so is this one good or bad? I don't know. Okay. Whereas if it was 4 to 7, all right, majority rules, and I'll decide that way. That, should I look at a lot of neighbors? Well, if you think of the picture I had before, as we added neighbors, we went further and further away. So they're less and less similar. It's usually nice to have big samples, but they're not going to be the same. They're going to be more and more different from each other. So if I go to smaller ones, I might be taking more risk, because maybe if I looked at just one, the closest neighbor, should I make a decision just on one other person? Shouldn't I look at a few? So it's tricky. And it varies by application. Typically what we'll do is we'll explore what would happen if I used 3 or 5 or 7 or 9 or 11. And how often I'll evaluate the performance of my model. How often am I making right and wrong decisions? And you may end up finding 5 is a nice number to work with. But it's a good trade-off between having more data to work with and but using only data that's really, really similar. Tricky. That we notice on this one with the employee, when I looked at a new case, I had to compare it to the 20 cases I already had. So suppose you trained your model and you built it using 1 million past customers. That's a lot of data to keep. And I'd have to go and then check my new case against all 1 million. That's an awful lot of data. Do I need all of that? And if I've got that much, a lot of it's probably old. Maybe that's data over the last 10 years. A customer from 10 years ago is different from one today. So maybe I should just keep the most recent. That it's really tricky with a lot of databases. If I'm looking at customer data, Amazon looking at customers, they've got hundreds of pieces of information. I know I mentioned in my face-to-face class, I applied for life insurance recently. Getting old, but still, I felt I needed some. And given my age, they're really hesitant to give you insurance. So they had a huge long questionnaire that I filled out. And then they came back with more questions and more questions. And then they sent a nurse around to take some blood, do tests on my heart, EKG things, blood pressure readings, that a whole bunch of things, as well as confirming that I was telling the truth on certain things about my height and my weight, other aspects of my physical health that she could observe. In the end, they had huge, massive number of different variables. If you're measuring similarity, you use all of them? We don't think of that. That's a lot to work with. It gets really complicated. And then how are you going to justify your recommendation? Oh, I look for a whole bunch of, I look for 5 cases that look similar. And based on that, I made a decision to give this guy a loan. Yeah. Should I believe you? How would you measure that they were similar? Where's your formula? And that doesn't make any sense to me. I don't know. It's there's a lot of others then that have to buy into your process. But it sure sounded good at the very start, and it works for real estate. There are a lot of choices that this seemed like a good idea at the beginning, but now I'm beginning to get skeptical about it all. That should I give different weights to different ones? Multiple regression gives, in a sense, different weights to different variables. How do I combine them together? Those distance measures that I had there, some of them look complicated. That there's an awful lot of challenges you get in doing this. But despite this, it actually works. It's widely used. It's very popular. And so it's not something that you'd rule out. There are many applications where this is the preferred strategy. That it's strange. To give you an example of this, we looked before at predicting whether or not someone was a student, and I took balance, rating, and income. Could I do this with KNN? So suppose I've got a target customer, got an income of 71,000, credit rating of 491, a balance of 1,350. How would I find a similar customer to this? So first off, I might try to think, is this target one that I'm looking at above average, below average? That the average customer has an income of $45,000, credit rating of 355, and a balance of 520. That our customer had an income that was 25,000, almost $26,000 above average, 136 points above average, and a balance that was $830 above average. So the units are quite different from each other that I've got in here, but I could go and scale these things and make them all Z-scores. So I'd have to divide through by the standard deviations of age and ratings and balances, and I get 3 Z-scores. So the Z-score is 0.73 for income, 0.88 for rating, 1.81 for balance. So how close are these to other customers? I've got to come up with a distance measure on that sort of thing. I happen, just for sake of illustration, to use Euclidean distance. And it's a little bit more complicated. Maybe I should have just used road distance. But anyway, that's what I did. And I did it for all the customers that I had in my database. Actually, what I did is the first case that I'm looking at is 1 out of my 400. And I took the other 399 and I tried to find someone that was similar to this first one I've got. And so I worked out all the Z-scores, and from there I calculated a similarity score. So of course, the first customer is the same as himself. So it had a similarity rating of 0. And then the next one was really, really close, a similarity of 0.16. And you can see it had a credit rating almost the same, balance really close, and had an income that was really, really close. And this one was a student, and the one I'm predicting turns out is a student. I'm going to try to predict, are you a student? The next few, though, were further away. Similarity scores were bigger, but I looked at the top 5 ones in terms of similarity. Okay. 2 of them were students, 3 of them were not. So I would have guessed this one isn't a student because I've only got 2 out of 3 that are students. So probably not a student. That, yeah, okay, I made a mistake with that one. Actually, 90% of the data are not students. So if you were in this crowd of 400 people and 40 of them were students, and you looked at people that were next to you, do you think the majority of them would be students? No. Maybe the students all gathered together, but probably no, because they make up such a small minority. To use this sort of approach like I just had, where I've got a decision rule of majority rules, then it should be balanced. I should have about 50% of the students, sorry, 50% of that group that I'm comparing to should be students, and about 50% are not students, and that would make it fair. So if I was comparing it to a data set that was made up of, say, 30 students and 30 that are not students, and then I looked at similarity measures, then that might work a little bit better. So it's more complicated again as to who I'm comparing it to. The first example I used had 10 good employees, 10 bad employees. So it was a fair game that time, but now it's not fair anymore. So let's just wrap up where we are right now, that it's a really common data mining application. And we have different types of methods. We've looked at 3 different ideas. 1, estimate a probability, apply a decision rule, and then do the classification. But estimating that probability sounds like value estimation, but standard regression is not the best method. Logistic regression is a lot better. Another method, let's just try to build a fence where most of the people on one side of the fence are in group A and most of the ones on the other side are in group B. We have a little bit of confusion in the middle, but I'm discriminating between the two by finding a way to build a fence. I'm not going to get into how do you build a fence. Or we could look at similar cases from the past. And if the majority of the similar cases are in group A, then we'll classify them as A. But if the majority are from group B, then I'll classify it as being group B. Seems to work. All of those methods are still being used on a regular basis. Some are quite old, some are new. Some have been refined and improved. They're a little more complicated than I show you. And there are a lot more methods, and we'll look at 2 more a little bit later when we get to chapter 10. There isn't a uniformly best method, that all of them have been successfully applied. It's less clear on guidance as to which is the best method with which type, if I'm doing a loan problem, what's the best method to use? If I'm looking at customer churn problem, what's the best method to use? It varies. That you might actually want to try several methods if you've got the time and resources to do that, and then test them out and see which one works best on your type of application. So don't lock yourself into one way to solve problems. Okay. So probability comes up along the way as we're doing this, both in finding a probability to assign a category, but also when evaluating it, since we make mistakes, we'd like to know, well, what's the chance that I'm going to make an incorrect classification? I'm going to make an error. So what's the chance that, among the ones that I classified as fraudulent, how many really are? What's the chance I'm classifying something as fraudulent when it isn't, or the other way around? That these are probability questions. And you really need to understand probability to understand classification, and especially in terms of understanding how to evaluate classification models. So we're going to digress from what we're doing now to look at probability. And you hear people talk about it a lot, but very few people understand it. Very few smart people understand it. So on Monday, I'm going to look at the language of probability and some of the rules that are used. Probably stuff you've seen before, you've seen it in high school, often taught really poorly. But I'll try to illustrate it just using actually data from a pivot table. But more complex problems, particularly decision-making problems, we get information and then we make a decision, and then we get information and we make decisions. And so there's often a sequence to things that happen. And these more complex problems, to use probability rules can be really difficult. We're going to look at one type of probability problem that's generally of the sort that things happen in a sequence. And we're going to look at how can we decompose those problems and analyze them without having to resort to formulas, if at all possible. That it's much more focusing on using our intuitive understanding of things to carry things out. But I'll also illustrate how our intuitive understanding of probability altogether is often very, very wrong. And often those mistakes are made by very smart people, experts, that how can they get things so wrong? And it's because the way our brain works and thinks about things is sometimes incorrect. It's backwards. But we'll show you with a couple of examples on that. And that's it. So there we go. Let's end it. Bye now.